Today we're looking at what happens when AI agents move beyond a text box. Once an agent has to hear a spoken command, watch a screen, or move a robotic arm, it enters a completely different world, one governed by real-time constraints. We'll walk through three domains where this shows up: voice conversation, controlling a computer, and controlling a robot. Let's be clear about what we're focusing on. Understanding a single image or a PDF is a solved problem. The model just needs the whole input at once, no special architecture required. Generating an image or video is also straightforward. It's just a tool the agent calls when needed. What's genuinely difficult is different. It's when information keeps streaming in continuously, and a response has to come back within a strict time budget. That's voice dialogue, screen control, and robot control. And that's our focus. The core architectural shift. There's one big idea running underneath everything we'll cover. A serial pipeline works like a factory assembly line. One stage has to finish completely before the next one can start. An end-to-end model instead goes directly from input to output inside a single system, with no handoffs in between. Why does this matter so much? In voice conversation, a pause of more than 2 seconds makes people uncomfortable. In robotics, a delay of just a few milliseconds can cause a collision. Those pressures are pushing every one of these systems away from pipelines and toward unified end-to-end models. Why voice matters. Voice is the highest bandwidth, most natural way humans interact with computers. Normal speech is about 4 times faster than typing, and it doesn't tie up your hands or your eyes. Because of that, voice tools are splitting into 2 categories. One is dictation, transcribing speech into text in real time as a kind of keyboard replacement. The other is a full voice agent, something you actually talk with and collaborate with, where voice is both how you give input and how the interaction happens. The most advanced version of this is simply talking through an idea out loud and letting an agent carry out the work. 3 paradigms of voice architecture. There are 3 major architectural approaches to voice AI. The first is cascaded, separate systems for detecting speech, transcribing it, generating a reply and speaking it out loud, each one passing the baton to the next. The second is end-to-end, sometimes called omni. A single model listens, thinks, and speaks, but it still waits for you to finish talking before it responds. The third is full duplex. The model listens and speaks at the same time, with no concept of taking turns at all. All 3 approaches are used in real products today, and the important question that separates them is, how does the system decide when you've stopped talking? Paradigm 1, the cascaded pipeline. The cascaded approach strings 4 stages together. First, voice activity detection waits for about half a second to a full second of silence to decide you've finished speaking. Then speech recognition converts that audio into text, which typically takes under half a second. Then a language model generates a reply, which can take anywhere from a fraction of a second to several seconds if it's doing complex reasoning. Finally, text-to-speech turns that reply into audio. Add it all up, and a short response can take 1 to 2 seconds just from this handoff chain. And that's before accounting for server load. When a server gets busy, wait times don't grow gradually. They spike sharply, which is why systems built this way struggle to stay responsive under heavy traffic. Making the cascade stream. You can speed this up without changing the basic structure. Speech recognition can produce a running transcript while you're still talking, instead of waiting until you stop. The language model can start speaking its answer in chunks as soon as the first sentence is ready, rather than waiting for the entire response. And speech synthesis can start producing audio from that first chunk immediately. All of this hides work behind time that would otherwise be wasted. What it doesn't fix is the fundamental wait for silence at the very start. That requires rethinking how the system detects when you've actually finished talking. Replacing VAD and ASR with streaming perception. Basic silence detection has 3 real problems. It's slow, because it has to wait to confirm you've stopped. It throws away information, since it only outputs a simple voice or silence signal, and loses all the emotional and tonal nuance in your voice. And it hurts accuracy, because chopping your speech into disconnected segments strips away context, which is exactly how something like an email address gets misheard, since the model can't use the surrounding words to disambiguate. The fix is a model that listens continuously and understands meaning and sound together, rather than treating transcription and comprehension as separate steps. Interestingly, when these systems misjudge whether you're done talking, the root cause is usually not the model architecture. It's that the training data was labeled using information the system could never have had access to in the moment. Fix the labels, and the problem often disappears. Paradigm 2. End-to-end omnimodal models. An end-to-end, or omni, model merges listening, thinking, and speaking into a single system instead of three separate stages. That preserves things a text handoff would lose: tone, emotion, the way something is said, not just what is said, and it cuts down latency. The trade-off is that a modular, cascaded system is easier to debug and tune piece by piece, while an end-to-end system is more of a black box and needs much more training data to get right. And there's a catch. Even omni models still wait for you to pause before responding, so they can still interrupt you if you pause mid-thought. End-to-end isn't always more accurate. Here's something that surprises people. Merging everything into one model doesn't automatically make it more accurate. It mainly makes it faster. If you compare a model that transcribes to text first and then reasons, against the same model reasoning directly from audio, the text-first approach often wins when the answer depends mostly on the words that were said. The direct audio-native approach wins when the answer depends on how something was said: tone, emotion, pacing. In one controlled test, a model correctly caught a math answer only after transcribing to text, but caught a speaking rate difference only when reasoning directly from audio. Same overall accuracy, but completely different failure points. The lesson is that you can predict ahead of time which approach will win, based on whether the task lives in the words or in the delivery. Paradigm 3. Full duplex and interactive models. Full duplex models drop the turn-taking assumption entirely. They listen and speak at the same time, continuously. One early research system modeled two audio streams in parallel, the user's and its own, achieving latency around 200 milliseconds, which is close to natural human conversation rhythm. A newer approach processes input and output in tiny slices of about 200 milliseconds each, so the model is always both listening and generating, deciding many times per second whether to speak, stay quiet, or interrupt. A production system built this way now handles well over 100 million users, and it can hold back politely while you're still thinking, use small acknowledgements like to show it's listening, and even handle live translation where listening and speaking happen simultaneously. Fast response versus deep thinking. Here's the core tension. People expect near-instant responses, but hard problems genuinely need time to reason through. There are three ways systems handle this. The first runs a quick response and a deep response in parallel with no coordination between them. The second lets the deep reasoning process quietly inform the quick one through a shared status update without speaking directly to the user. The third fuses thinking and speaking into one process entirely. None of these is simply better than the others. They're different trade-offs depending on how much latency you can tolerate and how deep the reasoning needs to be. Solution 9. Fast filler, slow answer. The simplest approach runs two processes side by side. A fast one gives an immediate holding reply, something like, "Let me think about that," within half a second. A slow one spends 5 to 10 seconds reasoning through the full answer in the background. This runs into two problems. First, it wastes effort and disrupts the conversation when the question was simple to begin with. The fast answer was already correct, and now the slow process repeats it unnecessarily. Second, and more seriously, because the two processes reason independently, they can flatly contradict each other. Imagine being told, yes, this plan is great for you, and then 8 seconds later being told, actually, it's missing a feature you specifically needed. That kind of self-contradiction destroys trust immediately. Solution 2. Interaction. Slow advice. A better approach lets the slow reasoning process see what the fast process already said and communicate through a private status channel rather than speaking to the user directly. The slow process becomes a background advisor rather than a second voice in the conversation. This is the most common approach in production voice products today, largely because reasoning models improve every few months, while a real-time conversational layer needs its own specialized training. Decoupling the two means you can always plug in the newest reasoning model without retraining the entire voice system. It still has limits, though. The fast process can misread a vague status update. It has no visibility into the reasoning happening in the background while it's still in progress, and fundamentally, it's still think first, then speak, rather than genuinely thinking and speaking at the same time. Solution 3. True thinking while speaking. The most advanced approach builds reasoning directly into a single model, so it can genuinely think and speak simultaneously the way people do. This relies on two mechanisms working together. The first ensures the model is reasoning about the actual sound, pitch, rhythm, tone, rather than taking a shortcut and just reasoning over a text transcript of the words, which is a surprisingly common failure mode. A model asked to judge a song's emotion will often just read the lyrics rather than actually listening to the melody. The second mechanism splits the model into two parts that run in parallel, one continuously formulating what to say next, and another immediately turning each new piece into speech, so a person can begin speaking a sentence before they've fully finished thinking it through. In a working example, the first audio is produced in about a third of a second. The cost is that a single model now has to be both the best possible reasoner and a fluent real-time speaker at once, which means retraining it every time either capability needs to improve. The fast-slow interface beyond text. When a fast process and a slow process need to share information, a plain text summary is easy to build and debug, but it's a narrow channel. A lot of nuance in the slow process's reasoning gets compressed into just a sentence or two. An alternative is to connect the two models directly at the level of their internal representations, using a small trained bridge that passes rich signal between them instead of squeezing everything through words. In game-playing experiments, this direct connection substantially outperformed the text-based version while adding only a few milliseconds of extra delay. But there's an important limit. This only helps when the real bottleneck is reasoning quality, when the fast process genuinely can't figure something out on its own. If the bottleneck is just raw reaction speed, no amount of shared reasoning helps, because the problem isn't a thinking problem at all. More human-like speech synthesis. Perfectly smooth, fluent speech with no pauses or hesitation actually sounds robotic, because real human speech includes pauses, filler words, and small hesitations that signal, "I'm thinking" or "I'm not fully certain." One way to recreate that naturally is to have the response-generating model output small control markers alongside the words themselves. Signals like, "I'm thinking here," add a pause, or "sound happy," or "slow down." The speech synthesis system then treats those markers as instructions, generating an actual pause, a sigh, a laugh, or a shift in pace and tone to match. This can be built either with a custom speech model trained to understand these markers natively, or, more quickly, by recording a library of reference audio clips, covering different emotions and speaking styles, and selecting the closest match for each marker. Computer use, the perceive-think-act loop. Now let's shift from voice to vision, an agent operating a computer the way a person would, by looking at the screen and controlling the mouse and keyboard. The core loop is simple. Take a screenshot, have a model look at it, and decide what to do next. Carry out that action, wait for the interface to respond, and take another screenshot. 3 things make this work well. How many kinds of actions the agent can take, how it locates the right thing to click on screen, and how the underlying model turns a screenshot into a decision. Visual grounding, finding the right element. Finding the right button or text field on screen is one of the hardest parts of this problem. There are 2 broad strategies. One turns it into a multiple-choice question. Every clickable element on screen gets a number, and the model just has to pick the right one, which is much easier than guessing exact pixel coordinates from scratch. Within that approach, you can either use a vision model to guess which regions of an image are interactive, which works on any interface including games, or, when you're working with a web page, read the underlying structure directly, since the page already knows exactly where its buttons and text fields are. This is far more precise. The other overall strategy skips numbering entirely and has the model predict exact screen coordinates directly, though this requires carefully matching the screenshot resolution to what the model was trained on, or its coordinate guesses will drift. Beyond static screenshots, watching and listening. Most systems assume the screen is basically frozen between one screenshot and the next, but real screens play videos, flash notifications that disappear in seconds, and carry audio from meetings. All things a system that only glances at the screen every few seconds will completely miss. The fix is to separate observing from acting. Continuously watch for meaningful changes using a very lightweight detection step. Only transcribe audio when there's actually sound to transcribe. And, this is the key part, immediately convert anything noticed into a short written description that persists even after the original image is gone. Across a range of models, adding this layer produced large accuracy gains, with the biggest improvement on tasks involving audio, since those systems previously had no way to hear at all. Mobile and ecosystem barriers. On mobile devices, the technical details shift. Instead of mouse coordinates, the agent uses the phone's built-in accessibility tools, and instead of clicks, it works with touch gestures like taps, long presses, and swipes. But the bigger obstacle isn't technical at all. Most consumer apps make money through attention. Ads you see while scrolling, products you're nudged toward, impulse purchases along the way. An agent completing a task on your behalf skips all of that. It ignores the ads, ignores the recommendations, goes straight to the goal, and leaves. For a platform built on advertising revenue, that's a direct threat to its business model, and that kind of structural conflict is much harder to resolve than any technical restriction. Computer use's unsolved problem: speed. Success rates on realistic computer use tasks have climbed close to human-level performance, but succeeding isn't the same as being fast enough to use. These systems typically need far more steps than a person would, and each step actually gets slower as the task goes on, because the amount of context the model has to consider keeps growing. The root issue is that the system can't think ahead. It can't plan its next click while still carrying out the current one. There's no complete fix for this yet, but there is a proven workaround. Run a fast conversational layer and a slower action-taking layer side by side, connected only through a running text summary of progress. The fast layer talks to the user in real time, while the slow layer actually operates the browser, and it only reports the task as finished once that summary confirms it's actually done. In testing, this made voice responses roughly 15 times faster with no drop in success rate. But remove that shared text summary, and the whole approach collapses, because the two layers have no other way to pass information to each other. Robot manipulation. Hardware isn't the bottleneck. When a low-cost robot is remotely controlled by a person wearing a VR headset, it can smoothly perform a wide range of household tasks, with response times fast enough for natural physical interaction. That tells us something important. For tasks that mainly rely on visual feedback, today's affordable hardware is already good enough. The limiting factor is the decision-making software, not the robot's body. That said, this claim has real limits. Tasks that depend heavily on precise touch and force feedback, or that need dexterous hands, still run into genuine hardware constraints. Two-layer architecture, planning and control. Robots handling complex tasks need to think on two different timescales at once. A slower planning layer breaks a high-level goal, like cleaning a kitchen, into a sequence of subtasks: clear the counter, load the dishwasher, wipe the surfaces. A faster control layer handles each individual action moment to moment, continuously translating what it sees and what it's told to do into precise movements. This mirrors the fast and slow pattern we saw in voice, but split along a different line. Not thinking versus speaking, but deciding what to do versus actually doing it. And the real-time pressure doesn't go away, it just moves down into that fast control layer. One key technique there is generating a short batch of future actions in a single inference step, then executing them one after another at high speed, trading a bit of responsiveness to sudden changes for much smoother, more efficient motion. VLA control models and generalization. The systems that translate vision and instructions into robot movements generally fall into two camps. Some fine-tune a large vision language model directly, having it output actions the same way it would generate text, one token at a time. Open versions of this approach are trained first on a broad mix of demonstrations, gathered from more than 20 different robot platforms, learning general concepts like grasping and placing, and then fine-tuned for a specific robot. A persistent challenge across all of these systems is speed. Traditional robot controllers run 1 to 3 orders of magnitude faster than these models can produce decisions. The standard fix is the same batching trick from the previous slide. Generate a short sequence of actions per inference and execute them rapidly, rather than requesting a fresh decision for every single movement. Most of these systems are trained by imitating human demonstrations, rather than through trial and error reinforcement learning, since reinforcement learned versions tend to master one task extremely well but generalize poorly to anything new. Cross-cutting themes. A few patterns show up again and again across every one of these domains. Systems keep moving away from rigid, rule-based turn-taking toward continuous, always-on perception. Fast and slow decoupling. A quick, responsive layer paired with a slower, deeper reasoning layer shows up in voice conversation, in game-playing systems, in computer control, and in robotics. And there's a simple diagnostic question that applies everywhere. Is the bottleneck that the system can't figure something out, or that it can't react quickly enough? Those are two completely different problems with two completely different fixes, and misdiagnosing which one you're facing is the most common design mistake in real-time AI systems. A few open questions worth sitting with. Real-time understanding of continuous video remains largely unsolved. Where do you see that heading next? Which of the three fast and slow strategies fits the latency budget of the systems you're building? Where might a richer, non-text channel between a fast and slow component replace a simple status update in your own work? And what would it actually take to soften the ecosystem barriers around automated computer use, better technology, or a fundamentally different business model? These are the frontiers still being worked out, and they're a good place to end.